Hi everyone, and welcome to today's talk. We are hosting Professor Morteza Gharib from GALCET, from Graduate Aerospace Labs at Caltech. And without further ado, I will pass on to him to hear about the Morse helicopter. Thank you, Mori, for accepting this invitation.
Absolutely. Thank you very much for inviting me to give this talk. I tried to stay within 1 hour, but since this is really extended talk, I may have to skip some of the slides, and I would like to apologize for that ahead of time. So the title of my talk is Mars Helicopter, or the Legacy of Theodore von Kármán. As GALCET stands for Graduate Aerospace Laboratories, and it's basically the aerospace department at Caltech, California Institute of Technology. And our story starts with Theodore von Kármán. Von Kármán was already famous for many achievements. In 1920s, von Kármán was known in European aeronautical circle for starting with his thesis was nonlinear buckling of columns and shells and use of plasticity in a structural collapse. That was his PhD thesis. Then came along von Kármán plate theory, and then he was heavily involved with Zeppelin, the airship company in Friedrichshafen on Lake Constance. And also, even at that time, he was a pioneer in promoting swept wings. Von Kármán became really famous as a name when he basically succeeded to explain the why vortex shedding behind bluff bodies like cylinders or any structures, even islands at really different Reynolds numbers, they have these staggered patterns. And he used a simple linear stability model in order to explain that. And in that respect, he got the big credit. Even they named the vortex patterns behind bluff bodies as Kármán vortices. And of course, these structures have been observed before von Kármán, but he was the one that actually explained why they are not symmetric and why they're they're asymmetric. And then he went on to explain the vibration of the electrical transmission lines and chimneys, Aeolon harp sounds that the electrical transmissions make under wind, and also suspension bridges. And later on in his life, actually, unfortunately, with a bad, I would say, unfortunate event of collapse of the Tacoma Narrow Bridge in 1940s, and he was able to explain that. But I believe that one of the most fundamental contributions that von Kármán has made was the establishment of the graduate aerospace, at that time graduate aeronautical laboratories at Caltech, which is even today it's a leading research center in mechanics of fluids, solids, and propulsion. It was started by a grant or endowments by Daniel Guggenheim Foundation to establish an aeronautical school in Southern California. Funded in late 20s by Theodore von Kármán, who became the first director of GALCET. Director in that terms, both was the head of department, chair of department, or at that time, or here even now, executive officer of department. And due to his vision and the plans that he had for establishing this department, even today it's spawned and sustained U.S. aerospace industry and ensured its the prominent position for decades. It was built. Von Kármán actually was hired as a consultant 2 years before he joined officially Caltech to design the 10-foot tunnel, which was kind of a larger scale of what he designed in Aachen and in Göttingen before he came to US. And the wind tunnel was finished in 1930s and was operational until 1998. Then was replaced with a more modern wind tunnel. Every US airplane flown between 1935 and 1945 was tested in this tunnel. And it can be said that it was responsible to bring or establish the aerospace or aeronautical industries in Southern California. And it was really used until 1960s, until most of the aerospace industry moved their basic research and wind tunnel testing because of IP issues to their own facilities. But I think that also another contribution of von Kármán to space science was started when a student from Texas A&M by the name of Frank Molina came to Caltech in 1934. And Molina was a graduate student of von Kármán. And then he had some very strange friends. One of them was Jack Parsons. He was a self-styled chemist, not a student at Caltech, and by Edward Foreman, who was a hobby rocket fan. And then there was joined by another graduate student, Apollo Milton Olin Smith, also known as Amos Smith, and then another graduate student, Hussein Sien, in 1936. And there was an interesting bond among these five, and their love of rocketry and encouragement from von Kármán. They started to work together, and basically started to test different, the rocket boosters, and right at the middle of the campus. And in that respect, they called them the Suicide Squad, and I will explain why. They basically they started to test these rockets, the boosters, right outside our building, Firestone building. And they had a very primitive system, like it was a big pendulum, and they hung the rocket underneath and then fired it. And then from this angle, they measured the thrust. And in one of those experiments, a rocket exploded. And unfortunately, at that time, they were running the wind tunnel. And when the wind tunnel, 10-foot tunnel, was running, the whole building was under pressure. That means pressure was lower than outside. And it sucked all the soot and whatever that came out of that explosion into the building and almost ruined all the instruments. And here comes really the interesting characteristics of what von Kármán was. So instead of kicking all these students and hobbyists out of the campus and terminate their affiliation, he went to them and said, "Look, guys, I think rocketry is important. So we bought a piece of land in north of Pasadena. It's called Flint Ridge, and you guys should go over there and do the testing, continue testing over this." And this picture actually shows that how they picked up a part of the sand, which was a riverbed, and sandy riverbed, and started to do the testing. And it's interesting that they started this process in 1936 and officially formed called the lab Jet Propulsion Lab, or JPL. And von Kármán was unofficially picked up as the first director, but later on he became official director of the JPL. Now, the group, the Suicide Squad, then later on continued their work, and they started many fairs in the rocketry in the US. And they also started the first startup in the US, I would say, raised a little money and started a company called Aerojet that exists even today. And it's one of the world's first rocket companies that was formed to go commercially. And they used these rockets they invented to help airplanes to have shorter takeoff distance. And they call it JATO, Jet Assisted Takeoff. And then they started other, businesses as part of the Aerojet. Now, JPL went on to do many firsts. The Explorer 1 was the first satellite launched by the United States, was actually designed and built at JPL and Caltech. And actually, JPL was called Project Number 1 of GALCET. So actually, the satellite is sitting on a shelf in GALCET for at least 8 months before U.S. Navy decided to use it, and with the Explorer. And that was in 1958. Von Kármán went on to receive the first, or be the recipient of the first United States, the science of the Medal of Science, and practically became a first major consultant to the DoD, especially Army, and stayed in Washington D.C. most of the time for the last 10 years of his life. And JPL went on to become a U.S. federally funded research and development center managed by Caltech, and is one of the 10 NASA centers. And currently, it operates 22 spacecrafts, 2 rovers, and 10 instruments in space, responsible for many space firsts, as you see in this slide. To first satellite spacecraft to Jupiter, Mars, and many others. The one of the most recent, the adventures of JPL was Perseverance rover. Basically, it's a Mars rover that designed to take samples and eventually return it to Earth. And it was launched successfully on July 30th, 2020, right at the middle of the COVID pandemic in the US. And it was very successful. And what's interesting is this rover had a little companion, a guest with it. And that guest was the first Mars helicopters called Ingenuity. The Ingenuity Mars helicopter is a small autonomous aircraft, and it was sent to Mars to perform experimental flight tests to determine if powered controlled flight at Red Planet was possible. And it still is operating. This is 2024. It is very interesting design. It's a coaxial double blade helicopter type design, and it overcame many challenges that, according to some experts, almost impossible at that time. But the group of engineers at JPL and Caltech together actually made for this little the flyer to fly on Mars. Now, you may ask why double blades. First of all, double blades have been used before. It wasn't anything new. You can see that George Kiley in 1796 had a design like that. Of course, that you can see many helicopters and also drones have it. It allows to have torque cancellation, and for payloads that require to be small, provided the compactness and also redundancy because of double blades. Disadvantage of such systems is that they have lower aerodynamic efficiency, and they're more complex in terms of the machinery that to drive. And also in power, you can see that, the power is usually torque times the flow through the disk of the blades. And if you have two different blades, you expect to have double the power and the torque and of the single one. But when you combine it, you can show that because the disk area remains the same, the while you can actually calculate the disk speed, that means flow that goes through the disk, then the efficiency, the power requirements actually much higher than when you have actually much higher, I mean, the square root of 2, much higher than if you have two single blade separately operating. So even though efficiency was not good, but it provided the torque cancellation. Otherwise, you should have a tail to cancel the torque. And it also provided the compactness, which is really important in terms of, how payload can be put together as part of the original rover. So it's successfully flown, and it provided many firsts, and we go through my talk through it. But what's interesting is that 100 years earlier, in another pandemic known as the Spanish flu, nothing to do with Spain, but somehow they call it Spanish flu, von Kármán was working on that with the Zeppelin company, and he was tasked to actually design an observational platform, manned or unmanned, to be tethered and to be able to use for monitoring the battlefields for at that time of the German army or Prussian army. And the idea was that instead of using balloons, that they are much more of larger footprints, to use a system that is harder to bring it down. So he and his engineers, Petrosky, Kármán, and Zorovic, they designed this helicopter-like observational platform for scouting. And this is exactly the same mission that Ingenuity has, to scout for the rover. And they, successfully flown and used it during the World War I. And this is interesting, that they built both the manned and unmanned version of the same system that they used. And what is interesting is that to look the similarity in design of the Ingenuity and the PKZ, the observational the platform. It's interesting because von Kármán designed that one, and his students at formed later on they basically formed JPL, and later on the GALCIT. They also came down with the same design, almost the same design, and that similarity, was quite interesting. That whether there's any relation or not, but even the serendipity of it was fascinating to us. Now, to show you a little video, I would like you to pay attention to this little machine here. And this is a real video of how Mars helicopter actually flown in Mars's atmosphere on Mars. Very stable and provided very interesting, the images that usually it was difficult for rover actually to go to the regions of interest, that almost impossible for rover to climb or go take a look at, say, a volcanic the areas. So but it wasn't as simple as I described. It provided many challenges. For example, the idea was to prove that powered flight in thin atmosphere of Mars was possible. The red planet has lower gravity, of course, 1/3 of the Earth, but its atmosphere is just 1% thick as of compared to atmosphere of our atmosphere on Earth. So also to demonstrate that miniaturized flying technology is possible, you can pack enough power, battery, and the aerodynamic efficiency to be able to take off. And perhaps the most challenging part was also operating autonomously. Ingenuity could only use solar power to charge its batteries, each test flight, and for each flight. And it should be performed without real-time input because it takes almost 14 minutes for the signal from operator goes to Mars. So to provide any command. And all those three each one of them could have been a big showstopper for us. Now, so at JPL, in order to study the performance of this flyer, they have any flyers. They have this environmental chamber. It's about 27 feet wide, 85 feet tall, and they could basically simulate Mars's atmosphere. And that table shows that the pressure of the Mars compared to Earth, and the test section or test ambient chamber was close to 1,000. We could bring it down. The density, we can get very close to what Mars's atmosphere has, and if you look at it, the kinematic viscosity also could be very close compared to what we see in Earth. Now, the point here is that even though we brought the pressure down, the density down, but chemistry was different because Mars's chemistry is more CO, CO2 compared to Earth's is more nitrogen. So, but from performance point of view, it wouldn't make any difference. Now, in that environmental chamber, so that we could simulate the Mars's atmosphere, you can only go up and down. But for a Mars helicopter, it was important that to be able to do the cruising, to be able to move around. So for the software control software, you needed to perform hovering plus cruising. So hovering was possible in this chamber, but cruising was almost, we have only 27 feet. And also would have been dangerous to try to avoid the walls of this big tank. So JPL engineers, approached me and said, "Look, can you build a wind tunnel or that can simulate Mars's atmosphere?" I can imagine that my first reaction, 1% density, it's going to be difficult. But no, let us look at it. And I had the very group, important, I would say, clever group of students that when I proposed to them, they didn't, even blink, and they said, "Yeah, we take the challenge." And the reason was that because the same group of students have together, they designed another type of wind tunnel that I'm going to go over it, and you see how we could transition from a wind tunnel for Earth to a wind tunnel for Mars's atmosphere. Chris Doherty, Marcel Weissman, my graduate students, and Jason Rabinovich, a graduate student of Professor Beverly McKean, and then the undergraduates, Alejandro Zavala, also was involved, and the chief engineers at JPL, Amy Kwan, who was the project manager for JPL site. So, of course, she had the army of the students and not students, I mean engineers that could help us for design and implication of the tunnel. Now, we have a center at Caltech, it's called CAST, Center for Autonomous Systems and Technologies. And in the CAS, we designed a very unique type of wind tunnel. It's a wind tunnel with, in this case, it's about 10 feet by 10 feet, and it has about 1,296 individual fans clustered in 9 by 9, groups, and the tunnel, I would say, or fan wall, could operate either vertically or horizontally or any angle in between. And and we could, as you see, we could control each fan individually to provide all kind of different flow conditions. And here is it shows the operation of the tunnel as it goes for different angles. And so we could basically do hovering by blowing the air just vertically against the gravity, or use it vertically as your normal wind tunnels. And you can see here that it's in a large the arena, and so we test different drones or systems that they need to see different flow conditions like gust or shear. And I'll let you watch this for a second. It's quite impressive. And these are all designed by graduate students. And of course, we had the outside contractor that built some of these components and was put together here. Now, this tunnel, as I mentioned, can provide vertical flow, horizontal, and different shear, uniform, as I said, gust, or random turbulence. So you can see this is, for example, what you see on the screen, and you can basically put random turbulence in it or shear, as you see in this plot, and to provide different conditions. And so control softwares should be able to handle this under different conditions on Earth, or later on you will see on Mars. The whole tunnel, the environment that we have motion captures, and we have all kind of different from PIV to laser Doppler to all kind of flow characteristics, as it's required by the researchers in the group or in the department. Here it shows that they actually put the Mars helicopter on Earth's atmosphere. And here you can see some of the studies they did. It's on a force balance. But I think the challenging part was how to duplicate this wind tunnel for the environmental chamber, the JPL. Here you see the picture of it. This is actually the size scale, and this is actual picture of the fan wall that's inside the tunnel, and it's about the 1.7 meters by 1.7 cross section. It can go up to 11 meters per second, right within the range of kind of velocities that we expect to for the Ingenuity to operate on Mars. And each individual fans could be monitored. This is a close up, and it was on a force balance, and later on was flying without any tether inside this tunnel. Now, one might ask, how did we design this tunnel? So we used a very simple, basic band laws that considering that the efficiency is the same, we can then get the ratio of the flows. Q1 is on Earth, Q2 is on Mars. So we can use different basically the densities, diameters, different rotations, and these non-dimensional parameters are what people use, not for just Mars thing, but actually for design of the helicopter and the blades and so on and so forth. Now, what is interesting here is that in these calculations, we assume the efficiency is the same, but in reality is not. The reason being that the Reynolds numbers that we usually operate, especially in Mars, are really low. So you're talking about, Reynolds numbers are not more than 10 to the fourth. I mean, this is, for example, our Reynolds numbers that we expected the Ingenuity to operate. And because of that, the flow is very laminar on the blades, and they're very prone to flow separation. So also the friction at lower Reynolds numbers are much higher. So you could see that the actual efficiency drops dramatically as you go from Earth to Reynolds number. It drops dramatically as you go from Earth to Mars, and then the eta also drops, and then the ratio of the power actually increases as you go to lower Reynolds numbers, and also the ratio of the flow and the pressure. So you can see that efficiency is pretty low because of you're operating a low Reynolds number, and this has been in detail. You can find in the paper by Weissman on experiments in fluids, published in 2021. So now you can see that this reflects back into how much battery power you can actually pack on the Ingenuity, and it was a big challenge. That's why the flight times are short. I had to stop and recharge again using the solar power. Now, the other problem that we faced was it's a well-known problem. It's called vortex ring states. So imagine that as you hover, if you are not in the proximity of the ground, it's okay. So there's practically the aerodynamics is because a disk model. But as you get close to ground, then at some point the flow that hits the ground being ingested back into, as you see in this artist simulation, back into the blade. So it creates a closed environment, is known as vortex ring state. What happens in a vortex ring state is that suddenly the thrust, goes down. So so as a result, the lift is not the theoretical lift, or at least the lift that you get as a reference. And that's a very dangerous state. And as we saw in the environmental chamber, it actually gets much worse as you reduce the density. So the question was, what should we do? So we embarked on some studies to identify what are these the vortex states. Also, another state that follows the vortex state as you increase the speed of the landing is called the turbulence wake state, which you don't ingest, but you create enough turbulence that the whole blade system start to shake. And that shaking is very dangerous because all the flight or control software that we had were not, even though we knew what happens on Earth, but we didn't know what happens on Mars. But we decided to design a new set of blades that can reduce the danger of going from the normal hover to safe hover, kind of bypassing the vortex, the state and the turbulent state. So the idea is that if you go too slow, you get trapped into vortex ring state. If you go too fast, you get to turbulent wake state, which creates lots of shaking. you need to basically go through that fast enough and get to a steady state that then you can land the Mars helicopter. And these are basically the standard, what you look at the textbooks. The question here is that can we design, a challenge was, can we design a different kind of blades for specifically to be able to bypass these dangerous states and go directly to. So Marcel, as part of his thesis, took that challenge to look at the different blade designs, and so he designed the miniature of the fan wall, and put the blades on the force balance, and then by changing the speed of the fans, he could simulate the different speed of landing or hovering down. And then later on, he actually flew it over the big tunnel and to see if the results of the tethered and untethered are equal in terms of performance of different blades design that he came up with. Now, also we used, the PIV, particle image velocimeter, to look at the actual what's the really physics behind this vortex state, and how this different design of the blades can avoid those states, and what's the physics behind it, so we could actually have a better performance later on. I can bypass this quickly. So usually what happens is that if you look at the thrust or lift of the blades, and as you change the climb velocity, you can see that there's always a minimum. This line here is where the vortex state is for different climb velocities. Now, if you can normalize it with the hovering, which is the reference, and you can see that they all collapse. And this region is the dangerous region because your lift suddenly drops. And if your controls software could not handle that, that means it's fatal to the whole the helicopter system. So now the question was, these are for reference commercial that you can get some of these blades. Can we design a different kind of blades that try to reduce this dip, so control softwares can do much better handling of these situations. He actually we tried different designs with all kind of different variations on different themes, the same themes sometimes. And then we went through all this process of changing the hovering speed, and based on that, see how we can reduce the vortex state, which was the gap or minimum that we saw. And then here are some of the results. And if you recall, let's go back here. I would like to draw your attention to B73 compared to other Bs here, and look at their performance. Now, if you look at here, in this basically row, we have the reference, which is a commercial, and then our designs. And you can see that most of them show this, dip, except one design that, is this one, B73. And let's look at the what is unique about that one. The trick was, if you look, sorry. The trick was that if you look at this design actually has very sharp or thin tip compared to all other designs. Of course, you could see the trend that as you get narrower and narrower, but it seemed that that one was the one that actually was the winner in terms of trying to get out of vortex state, which is this deep minimums. If you just pick up a commercial one, you're really in danger. So for especially then later on studies that computationally, we found that also for low density, this design was basically the winner in terms of performance. And you could see that here, the T minimum for E7.3 is about 94%, which is quite impressive. And for 8.1, let's go back and see which one was 8.1, is this one, which is completely flat. So we're kind of comparing to exaggerated designs. That was a big lesson, that most of if you look at the helicopter blades today, most of them are almost flat. So this was kind of unique in terms of discovery that we made, and which was not really well studied before. And compared to 8.1, we said it's 0.67, which is you lose almost, the 30% of the lift very quickly, and you needed to take care of that. Now, let me just go through this. It shows that, we normalize that, of course, the trust, and this is minimum. And you can see the minimum actually increases. That means this is very good performance. And anything we did over these commercial ones actually improved the performance of increasing the minimum. That means making it more flat. So these are more of this. You can see that we actually could make it really much worse than even the commercial ones, and that was 8.1. So anytime that we use the cord length, to increase the cord length, reduce the performance, taper it, increase the performance, having a pitch, increase the performance, but by increasing just a number of blades, it reduces that to a point that becomes a disc, no performance. So let me just, this is the compilation of all the results we have, which is actually a good design, the table for future if you wanted to get different performances. Now, the other things, remember the turbulent state, we were more interested on what kind of, let me just, on the turbulent state, we also realized that, this is the level of fluctuations. And so I think that I'm showing the wrong one, sorry. This, if you can allow me. Yeah, here. So here shows that, the level of fluctuations. Remember, turbulent state did not reduce much of the lift, but lots of fluctuations. So for that one, we fortunately realized that 7.3 actually has better performance in terms of fluctuation too. So it was kind of a strike of luck that that 7.3 actually reduced the residency in the turbulent state, also reduced the amount of fluctuations. Now this shows actually the fluctuations level. You can see that 7.3 still outperforms everybody else in terms of the fluctuations. I think that this part is nice because one thing we discovered was that the in the vortex state, if you do PIV, this is just the let me just look at it. And you look at the vorticity, you can see that the for vortex state and the turbulent state, the vorticity really accumulates around the tip, compared to hovering that actually flies up. And we believe that this accumulation of vorticity or sticking of the vorticity concentration near the tip is the key to the vortex state and the oscillations. While if you design the tip to be narrow, so there's not enough surface, then you have this, the flying out of the vorticity concentration. And this is the case of the when we had the 7.1, B7.1, the blade design. Now I'm getting to the close to my time, so I'm going to quickly go over some what else we want to do in terms of the ideas for Mars helicopter. So if you look at it, Ingenuity system mass about 1.8. We want to actually make it much bigger, so the payload almost for Ingenuity was 0. But we want to get to 5 kilograms in order to put cameras or other things that, sensors that can basically allow for better performance and to be able to actually carry more science, the instruments. And also the range is from 700 meters, we want to increase it to 13,000. And instead of 160 seconds, we want to go 600 seconds. This allows that basically the next helicopter to be a drone that replaces even the rover, if we can achieve that. There's several, I would say at least 20 proposals. Then they can categorize them to two. One is that add more blades, make the helicopter a drone, and just try to do it that way. So there's no driving around. It's more of flying, landing, flying, takeoff, landing. So, and this design actually has been studied also at CALTECH. In front of a wind tunnel, it had a jet assisted. In order to, you can guess now, in order to reduce or adjust the descent velocity in such a way to avoid the vortex ring state. So this project is ongoing and under considerations among others. But then we at Caltech at Center for Autonomous System Technology, we say, okay, why not think of a different approach? And that approach is that, okay, we have the Ingenuity, it's a good scouter, can go around and look at things, and the rover can go actually there and take the samples. And the idea was that what if we combine these two? So in that respect, it was a big challenge. You want to have a rover that can fly too. So we designed a system we call multimodal mobility morphobot, or also known as M4. And the idea was that to have a rover that can transform to be a flyer. So just think of the sample, the video. So the idea is that to be able to transform and to be able to go around autonomously. So another group of students, they designed this system, and as you will see, they did lots of testing. This is actually its first flight. You can see that lots of instability or instabilities. Now, this is actually a view that this machine that we designed autonomously goes around the campus here, sees the bushes, it has to go over to the lake, pond, and decides that, no, I want to be a drone now. So morphs from a basically car to become a drone. And this is basically all autonomously done. This is another one from the front view camera. It took off because the bush was in front of it, and then over the machine, over the pond, and landed, and then transforms into basically a car. And I think this is for us was a big challenge, because people ask, can it do other things? So because it has to go through narrow passages, it has to be able to change its shape more than just going from a flyer to a car. So it shows that, yep, realizes has to change its shape and to be able to go through these narrow passages. Or in this case, it can grab something, that hold it. So graduate students had a lot of fun with this, or to be able to climb without, if, for example, there's no way that the wheels can work. In this case, it becomes a Segway. That means you can actually stand up. This is good for observations. And still, this is a research project, but the fact that you could do that was and this by itself, it can very slowly lands. This one is that, this is an object, so it lifts up. The person over there is just making sure this doesn't go haywire. That's quite impressive when you see it in actions. Then I think I'm at the end of my time, and I would like to leave some time for any questions that the audience may have. Thank you very much.
Thank you very much for the very interesting talk, very interesting work. Audience, if anyone has questions, please feel free to either speak up or type in the chat.
Hi, sorry, I have a question.
Please go ahead.
Yeah. Hi, Marty. Thank you very much for the very nice talk. So I have a couple of questions. The first one is you mentioned the vortex ring state, and I'm wondering how much, because these are already present on the Earth's atmosphere for basically for all helicopters, right? So what was the difference you noticed? I can look up the paper too, but I don't know if you could just maybe tell us what was the difference between the blade designs that you noticed? What was the unique properties of the Martian environment that was, especially in relation to these phenomena?
Well, most of the information we have is about helicopters, and helicopters have slightly different scaling problem. So blades hardly get close to ground, correct? Compared to the scale. The drone of scale that we use, the ground effect is much stronger. Even though vortex state is well known by helicopter industry, but they hardly get to that state unless they have really the uplift flows or kind of thermal plumes that creates that. But for drones, every time they get close to the ground, that vortex state shows up, and it's a big issues for most of the from hobby drones to commercial drones. So that's why the blade design, to answer your question, so the blade design is more important for drones than for helicopters.
Okay. I do have one more question if I can ask, and then I'll mute myself. Did you notice a challenge with cooling the motors? And the reason I ask is we are running some tests with in a vacuum chamber to simulate Martian flight, and our biggest problem is cooling, and the motors tend to fail very, very often.
Absolutely, and that's an excellent question, and yeah. So the reason is that because of just low density, correct? And the heat is generated by the friction and magnetic field, but it definitely had heat transfer issues, even though the power required was lower, but heat transfer was a major challenge. And the way they designed the blade, actually, if you recall, is tapered, so they kept the thickness wide near the blades and near the motors. So they made sure that they always is circulation. But it's we don't know it's going to be a major issue for larger drones or not.
Thank you.
There is another question in the chat from Buhan, where his question is about whether co-rotating or counter-rotating systems would make a difference in the lift and drag characteristics of the blades.
If both blades, rotate in the same direction, then you have a torque issues. So definitely will change the aerodynamics too. But the counter-rotating is the main advantage of this coaxial system. So definitely will have a big difference, but we haven't tried because co-rotating is going to be, unless you put a tail, it's going to be almost difficult to test in any chambers. I hope I answered the question.
Sorry, because no one else is asking. I have one more question, Maury.
Sure.
Have you published did you change the methodology for doing PIV at these sort of low pressure conditions? And is the technique similar, or did you have to modify the technique to do PIV in these conditions?
We did not do PIV in the chamber.
Okay.
The reason being that anything we introduced at that low density would basically have lots of descent velocity, any particles, So that was an issue. We tried to do it, but it wasn't successful.
I think it's a very challenging. Yeah, that's a problem. Yeah, right. Okay, thanks.
Maybe I can ask another question regarding the setup, this grid of funds to generate the incoming flow. So for how long can the system run? So I was kind of thinking, would it have issues with heating because there are small motors, a large number of them running together?
I think the maximum was about 16 seconds.
Okay. So in the classical wind turbine setup, so it won't allow for any boundary layer to develop, right?
Yeah. The we use the actual commercial motors, and the people at JPL, because of time limitation, they had another design which a different, more efficient wounding, and they showed that it produces less heat, but we didn't have time to actually implement it for Ingenuity. But the next generations, they're going to be used.
Thank you.
Hi, Maury.
Yes, go ahead, please.
Yeah, sorry, can I ask one question if I have time?
Sure. Yeah.
Yes.
I mean, I have time.
Okay, yeah, thanks. So when I look at the photos that you showed about the wind tunnel that you created with multiple fans, thousands of them, it looks like the whole setup is in a room where your flyer is flying. So does it mean that the whole room is a vacuum chamber, or how do you maintain the density and pressure in that area?
Are you talking about the in the drone arena or in the vacuum chamber?
Your drone arena where you have 1,200 fans made for that particular wind tunnel, which can turn vertically or horizontally.
Yeah, so it's not in a room actually. I didn't show it. So basically, the flow goes out, so it has open exit.
Okay.
So, but we studied carefully there also because the air somehow goes around the tunnel. Okay, so we had we did lots of CFD and also confirmed it with our measurements. And maybe I can quickly go to. Do you see this?
Yes, that's exactly what I was asking.
So the side that I'm sitting right now, I'm looking at a tunnel, it's actually open to atmosphere.
Oh,
And
okay.
this is almost a 4-story building.
Okay.
So the velocity, return velocity going back to the fans is very small, very slow.
Right. But then when you think about the density and pressure, how do you compare the performance in these situations in atmospheric conditions versus those in the low density, low pressure?
Well, what's interesting, because we used hot wires for the vacuum chamber.
Okay.
And in terms of performance and turbulence, that by inherently they are high turbulence wind tunnels, correct?
Yeah.
If you get to 2% or 1.5%, you're lucky, because
Yeah.
unless you put a lots of flow management in front of the fans, and then because this is open both sides, you just stop the flow. So when we checked with the people that are experts on Mars atmosphere, it says, oh, 2% is nothing. When you have the Mars winds or something like that, you're talking that gas that goes up to 20% fluctuations. So they were very happy that we could simulate them at 2 to 3%. And uniformity was pretty good. This was about, almost, 95% uniform across.
Okay. Wow. Yeah. Nice. Thank you.
You're welcome.
Good day, Maury. I have a questions and actually, so I'm from Melbourne Uni. And actually, I'm working with your former student, Professor Lafi Zuhal from ITB. He sent his regards.
Okay.
He apologizes he can't join today. So, Maury, I got a quick question. Is there any future plan for any fixed wing in instead of rotary for a Mars activity? It's just my rough question because I mostly work at boundary layer, so I'm just wondering if there are an opportunity for boundary layer activities on Mars, for a fixed wing. Thank you.
Well, I've seen some proposals. Again, the problem is unless you really go to really high speed, high Knudsen numbers, it's almost difficult for getting any decent lift unless you have really large areas. So that's why, high RPM, the fans are perhaps the only way for now to be able to fly around Mars.
Understood. Thank you.
Well, thank you so much. If we don't have any other questions from audience, we may thank you again for the great talk and wish you a good night. And everyone in Australia, thanks for joining and have a good day.
Thank
You're
you.
welcome, and thank you for very engaging and having engaging audience that asked good questions and tough questions. Yeah. Thank you very much.
Thank you.
Thank you.
You're welcome.